Hello everyone. Today's lesson is going to be on what's called the chain rule. But before we get into the lesson part, just to kind of motivate where it comes from or why it's useful a little bit, in the homework take-up from the lesson on product rule, okay, there was a question kind of like this one. It was more complex, but basically you had a factor that was squared. So the first thing to note when trying to take the derivative of this is that, well, if it's squared, it really means I have the same factor twice. Okay, and now I can apply the product rule, right? So to do my derivative, I have the derivative first, which is 3 times the second, 2x minus 2, plus the first, 3x minus 2, and times the derivative of the second, which is 3. Now I could from here just, start distributing and tidying it up. Okay, but one thing we noted when we went through that homework take-up is that I really have the same expression twice here, right? Like this is the exact same expression, and you got to move this 3 over here to make it match perfectly, but right, it's the same thing twice. So I could tidy this up as it's 2 times, okay, 3x minus 2 times 3, because I have 2 groups that look the same. Okay, but if we have a look back at our original function here, okay, look what I started with. I had 3x minus 2 squared. Okay, we know that if I just had something like x squared and took the derivative, we just bring the 2 down. Okay, and it looks like that's what happened here, right? The 2 came down, okay, and I left the expression alone. Okay, and what's this over here? Well, this is the derivative of the inside, okay? So maybe there's a faster way I can do this. That instead of having to write out the square, right, expand it out and do product rule, maybe I could have went straight to this line by bringing down the 2 and doing the derivative of this. Okay, and that's essentially what chain rule is, but we'll delve a little bit more into that as we go through the lesson. Okay, so for this, we're going to review something from advanced functions. Okay, towards the end of the course, you will learn about something called a composite function, right? F of g of x. It's an open circle, it's not an O. This is not a fog function, but it means take g of x and substitute it into f of x, right? So, taking one function and putting it inside another function. Okay, so to review what that looks like, for example 1, we're just going to take these 2 functions, and we're going to find f of g of x and g of f of x. Okay, so for the first one, right, f of g of x. Okay, it literally means f of g of x. Okay, so again, I'm going to show this in very detailed steps. And if you see what's going on, you can skip a couple lines here, right? What's my function g of x? It's 2x plus 1. So this is what's f of 2x plus 1, right? So that means I take 2x plus 1 and put it where I see x in my function. So I now have square root of 2x plus 1. Okay, let's do the other one. So to do g of f of x, that means I'm going to do g of f of x. So I do g of square root of x, which means I go to my function here and replace x with square root of x. So it's 2 root x plus 1. Okay, so yeah, when I change the order, I got different functions there. Okay, so now let's try to take the derivative of those 2 functions. And I'm going to flip over to the last one I created as my starting point there. Okay, so if I want to take the derivative of this, so g of f prime of x. Okay, well, actually, before I do that, I might want to remember this is x to the power of 1/2. And now I'm ready to start taking my derivative. Okay, the power 1/2 comes down and multiplies with a 2, so that becomes a 1. And my power reduces to a 1/2, so I have x to the negative 1/2. And then my constant, that derivative is 0, so it's just x to the negative 1/2, which is 1 over square root of x. Okay, that wasn't too bad. We'll set up the same thing here. So my first step would be say, okay, this is 2x plus 1 is negative 1/2. Sorry, not negative, that's just 1/2. Okay, well, can I use the trick that I just did here? Okay, no, right? I don't currently have a rule that lets me do this directly, although we kind of hinted at it in the example at the start. Okay, right? This isn't a product rule. You know, I can't write this expression out half times. Okay, so that doesn't really work either. Okay, so, but let's pretend for a second. If we use that same idea we talked about at the beginning, okay, what if all I have to do is bring down the 1/2? So I bring down the 1/2, I leave my expression alone, okay, and I make this negative 1/2. Okay, and then what we would have to do is figure out the derivative of what's in here. Okay, so the derivative of what's in there is 2. Okay, and now I can tidy this up. Okay, 1/2 times 2, that's 1. Okay, and the power of negative 1/2 means it's going to be 1 over square root of 2x plus 1. Okay, so this little trick that we used, okay, it's harder to verify how that worked because I can't show it another way. Okay, but this is essentially kind of what the chain rule is, and that's what we're going to define now. Okay, so if you have some function h, which is the composition of two functions, f and g, okay, and f and g are differentiable, right? We know how to take the derivative of those two functions. Then the derivative of h of x is f at g of x times g prime of x. Sorry, f prime at g of x times g prime of x. Okay. So the derivative of a composite function is equal to the product of the derivatives of the two functions. I need to fix that. Bear with me a second here. Okay, I'm not sure this wording is any better, right? It's the derivative of the first function, right, of or at the second function times the derivative of the second function. Okay, so the key skill here is going to be identifying what's your outer function, what's your inner function, and then following the pattern. Okay, in Leibniz notation, we write this a little bit differently. Okay, we say if y is f of u and u is g of x, right? If I plug in g of x for u here, I have the same thing, f of g of x. Okay, then dy dx is dy du times du dx. Okay, so to illustrate what I mean by that, we're going to redo example 2, that second part, with this kind of notation. The idea being is I introduce a change of variable and then do the parts separately. Okay, so for that Leibniz notation, this is how I would set it up. Okay, right, we knew that f of x in this case was square root of x, and that g of x equals 2x plus 1. Okay, so I'm going to let u equal g of x. Okay, so that means my functions now, I have f of u is square root of u, okay, and I still have my g of x. Okay, so dy dx equals dy du times du dx. Okay, and actually there for reference, u is g of x, so u is 2x plus 1. Okay, so my first part says, what's the derivative of y with respect to u, right? So I'm using this function here. And actually, go back up and change that to y. Okay, so the derivative of y with respect to u. Okay, well, that is equal to u to the 1/2. So we know how to do that. Okay, that derivative is 1/2 u to the negative 1/2. Okay, times du dx. So here's my function u. Okay, and it's equal to 2x plus 1. So the derivative of that is 2. Okay, so now I do some tidying up, right? A half times 2 is 1, so that's gone. Okay, u to the negative 1/2 would be 1 over square root of u. Okay, and last but not least, okay, I can put that back the other way. So I know that u is equal to the square root of 2x plus 1, and there's my final answer for the derivative. Okay. So I'm going to go through a couple more examples. Okay. I don't really have a preferred method. Pick the one you like best. Okay, you do need to be a little bit familiar with the dy dx method because later on we're going to be using this in a certain context. Okay, so you need to be familiar with it, but whichever one works better, I'll suggest you practice that one more. Okay, so here's a couple of functions. Actually, I'll move this one, and we'll do it both ways. So the first way to do y prime, okay, is to say what's my outer function and what's my inner function. Okay. So one way to help you think about that is think about bed mass, right? If I had a value of x and wanted to work this out, what would I have to do first? Right, well, I'd have to complete the work inside of here first, okay, and then I would do this second, right? So that means that this part is my inner function, okay, and the power 3 is my outer function. So this is my f of x, right, is something cubed. Okay, my inner function, this is my g of x, and that's that expression inside the brackets. Okay, so how do I do the derivative of something cubed? Sorry, I do the outer function first. Well, I bring down the 3, okay, and I reduce the exponent to 2. Okay, and I leave the inside alone. X squared plus 2x plus 3. Okay, then I multiply that by the derivative of the inner function. Okay, what's the derivative of the inner function? Well, the derivative of x squared is 2x, and the derivative of 2x, okay, is 2. Okay, and technically, I can stop there, right? If you wanted to, you could expand and simplify it, but basically, my derivative is 3 times x squared plus 2x plus 3 squared times 2x plus 2. Okay. And one of the advantages to leaving it like this and not expanding it out is that if for some reason I want to know, say, roots, right, it's already partially factored, okay, and I can work with it from here. Okay, so that was the first way. Let's show how it works with the other notation. So this time, I'm going to kind of explicitly write my functions. So my outer function was something cubed. So y is equal to something u cubed. Okay, u is my inner function. So that's x squared plus 2x plus 3. So to figure out dy dx, okay, I do dy du times du dx. Okay, so I go over my function here. Here's u, my function u, it's u cubed. So what's the derivative of u cubed? Okay, that is 3u squared. Okay, times, here's my other function, okay, du dx. So what is the derivative of u with respect to x? There's 2x plus 2. Okay, final step, I just put my function u back into the function, or into my derivative. So that's 3, and u was x squared plus 2x plus 3, and then I square that times 2x plus 2. And that's the same expression we had above. Okay, we're going to do one more. Okay, y equals 1 over x cubed minus 1. So like we did before with rational, okay, we're going to change it to something involving exponent, so it's easier to see what's going on. So this is the same as y equals 1 over, pardon me, I don't want the fraction anymore, x cubed minus 1 to the negative 1. Okay. So what's my inner function? This is my inner function. Okay, and the power negative 1, that is my outer function. Okay, so for my derivative, y prime, I start with my outer function. How do I take the derivative of something to the power of negative 1? Well, I bring the exponent out front, and I reduce that exponent by 1, negative 2. Okay, now I take the derivative of my inner function. Okay, the derivative of x cubed is 3x squared, and the derivative of negative 1 is 0. So that part is done. Okay, now I just do some tidy up. Okay, negative 1 out front times the 3x squared is negative 3x squared. Okay, and the exponent, negative 2, pushes this back into the denominator. So this is over x cubed minus 1 squared. Okay, and that's done. Okay, so again, I'm going to show it in the other notation as well. Okay, given my function, okay, I had y equals 1 over x cubed minus 1. Okay, so my function y, okay, is 1 over something, okay, 1 over u. Okay, my function u is what's in the denominator, x cubed minus 1, right? If I substitute this into here, I get my original expression. Okay. And again, it would be helpful to say that's the same as u to the power of negative 1. So to do dy dx, I have to do dy times dy du times du dx. Okay, so derivative of the first part. Okay, so do dy du, derivative of u to the negative 1 is negative u to the negative 2. Okay, the derivative of x cubed minus 1 is 3x squared. Okay, again, I tidied that up a little bit. So I get negative 3x squared over u squared. And now I substitute my expression back into u. So 3 squared over x cubed minus 1 squared. Okay, and we're done. Okay, so it just takes some getting used to, right? Practice, get used to the method of how that works. So here's the homework. Okay, again, this first block, okay, I highlighted AC there, but all these questions are asking you, do the derivative, do the derivative. So again, do as many of them as you need to get the hang of it, okay? But that's the skill that you really need to practice here. Chain rule is probably one of the most important rules in terms of taking derivatives, okay? So thank you for watching. And of course, if you have questions, please send me a message.